Section of videos we're going to be exploring logarithmic and exponential growth models, and when you hear the word model, I want you to consider the fact that what we're trying to do is say that maybe there exists this real life relationship here. You know, we say over time, maybe the amount of a population over time, and maybe a population is growing exponentially. Now, does the population grow exactly this way? No, it doesn't, but we can actually put in some specific values like, hey, we started off with a population of this much and the growth rate is this much. And we can observe this because if we look at the data points, they kind of trend upward in this fashion. So our job a lot of the time is going to be comparing, two different quantities, some input and some output, and being given certain information and working out the rest of the unknowns. So it's really just an algebra lesson. Let's go ahead and take a look at these two examples here. I'm going to work through them pretty quickly, but it says the population P of a city is given by P equals 95,300. E to the power of, this is 0.055 t, where t equals 0 represents 1996. So we're modeling a population here. It approximately follows this model here where P is the population and T is the number of years after 1996. So we're saying at T0 we just started this experiment. So I say according to this model, when did the population reach 150,000? So I want to approach this both algebraically as well as graphically. We're going to talk about what this is here, but one thing I want to point out is this. In this video we're going to kind of focus on our two primary growth models, and these happen to follow the model some output or y values equals some initial value. So I'm going to underline this. A represents some initial value is what A represents. So initial value, that's A. Okay. Then we say E is our natural base, okay, and we say to the bx where B, let's make a little note here, B is the rate. So I want to make a comment on the rate here. We say if B, we consider it to always be positive here, then we say if I had a negative in front of a positive, it would be negative, but if I had a negative rate, we would be talking about decay. And if we have a positive rate, a positive rate, then we have a growth model. So anyways, moving on to here, we said we have two quantities here, P and T, where P is population and T is time. Look at the question we're asking here. It says, according to this model, when did the population reach 150,000? So what we've been given is some P value here. I'm going to write down this known we say is 150,000. Okay, and we do not know T. We want to find T though. If you read the last question, it says, all right, when, according to this model, when did the population reach 150,000? So algebraically, what we're going to do is we're just going to plug this in for P, and we get 150,000. I'm not going to write the comma that I think is not unnecessary, but it can kind of get in your way sometimes. So 95300, we say e to the 0.055 t. So the first thing we want to do, just like any time we solve an exponential logarithmic equation, is isolate the base, isolate the log. So we're going to divide both sides here by 95300, and I'm actually 95300. I'm going to knock off two of the zeros on top and bottom, and I'm going to say that these cancel out completely. And maybe I'll carry this over here a little bit, but we say e to the 0.055 t. Give me some license here to put e on the left now. And I'm going to put this quantity 1500 over 953 on the right. So we say 1500 over 953. What we want to do now is we want to write this logarithmically. We'll just do this over here, but we say what our base is here is e. So I'm going to write this in a way that you don't often see, but I'm going to say log base e. E turned into 1500 953rds. So we say 1500 over 953. That is log base e turning into this, and we took it to the 0.055 t power. So what this means now is we can actually divide both sides by this constant right here. We've got this thing back down the ground, so 0.055 t. And we say then t must equal this quantity right here. So this is our time, and this is in years. Now we need to actually find this. Now log base e, let's keep in mind that that's shorthand, would be ln. So if I get my calculator out here, actually get my calculator out and flip back over to here, this will help us out a little bit better. Here we go. Sorry about this. We say we're going to take 1500 953rds, so 1500 divided by 953 is this in here. We're going to take the ln of this, so we say ln of that is equal to this, and we're going to divide by 0.055, and this should give us our time. So 8.25-ish years. So we're going to say this time here, this time is approximately 8.25 years. But to answer the question, it says in which year? Well, keeping in mind that t equals 0 is 1996, then t equals 8.25 is 8.25 years later, would be 8.25 years later, that would be 2004 and a fourth of the way through the year. Okay, so January, February, March. You'd be in March-ish. Okay. We wanted to explore this graphically, and we've already got a time here where this is actually going to occur, but the way we're going to explore this graphically is we're going to go back to the original model, which said 15 you know, 1, 2, 3, 4 zeros was equal to 95300 e to the what 0.055t. And so what we can do is we can actually treat this as two different functions essentially. I'm going to go graph both, but I'm going to call this one f of x, and I'll call this one here g of x. But I've already got this model here graphed. And actually, I think when we flip over to the interweb here, we say 95300 e to the 0.055. I have to use x and I have to use y, and I've actually called this one f of x. Let me fix this. We said we were going to call it g of x. And our f of x was going to be the quantity on the left, which was 150000. And we're actually going to have to fix our window here. So let's go ahead and make our x-axis. We want to start at year 0. Why don't we do that? We say 0 out to, we ran into it like 8 years later, so why don't we go out to 10 years? That's a good thing. We'll go by ones. And then we say on our y-axis, well, you know, negative 5.374, that'll help us see the, well, let's go negative 10. That'll help us see the x-axis when we're going up to, like, you know, 200,000, because, you know, we had to go up that far to see the graph. So we say, why don't I go by, like, you know, going up to 200,000, we say 50 thousandths. You know, I'll go by that amount. Okay, and so I'm actually going to have to move this a little bit here if it'll let me. And if you zoom out, you can really see that this is a growth model over time. But you see two graphs here, and basically we're saying, okay, on the x-axis we have time, y-axis we have population. We say, when did this exponential growth model reach the height of this vertical line right here? And we can actually just look at this intersection. It says 8.247 years after the initial time. And looking at the initial time even, we say, look, it started at 95,300. So this is just an exponential growth model, larger numbers. So in the next video, we'll take a look at a problem where we're actually given some data and say that it follows an exponential growth model. You have to come up with a model yourself.